All right. So today we're going to take a fresh look at some of the stuff we covered in the last two lectures. And the graph I want you to keep in mind as we go through this lecture in terms of what to expect is this first time. And last Tuesday's lecture, we covered some stuff. I talked about a method for the sinusoidal response, which was agony. So I warned you it'll be agony. And then towards the end, I showed you another method that was quite a bit easier, but still pretty hard. And I promised you that today there'll be a new method, okay, which is going to be so easy it has to be almost right. Okay, just imagine. Okay, I'm going to make a statement right now that I think you will all find hard to believe. So what I'm going to say is that just imagine your RLC circuit. Okay, your resistor, inductor, and capacitor, a parallel form or series form. Imagine that you could write down the characteristic equation for that by observation. Okay, in 30 seconds or less. Just imagine that. By observation, boom, write down the characteristic equation for virtually any RLC circuit or RC circuit or whatever. And we all know that once you have the characteristic equation, you can very easily go from there to the time domain response intuitively, or to the sinusoidal steady state response too. Okay, so just keep that thought in mind. Okay, imagine 30 seconds, okay? And that's what you should expect in today's lecture. So students often ask me, so if this stuff is actually so easy, why do you take us through this tortuous path? Okay, so are we just mean? We just want to show you how hard things are and then show the easy way. I've argued with myself, every year as to whether just go ahead, give the easy path, and that's it. But I think the reason we cover the basic foundations is that it gives you a level of insight that you would not have otherwise gotten if I directly jumped into the easy method. All right? So you need to understand the foundations, and you need to have seen that at least once. And second, once you do something the hard way, you appreciate all the more the easy method. Okay? All right. So today we cover what is called the impedance model. First, let me do a review. Just because of the large amount of content in the last two lectures, I did them using view graphs. I usually don't like to do that. And but even then, it was quite rushed. So let me quickly summarize for you the main points. So we have been looking at, on Tuesday, the sinusoidal steady state response, also fondly denoted as SSS. And the readings for this were 14.1 and chapter 14.2. So what we said was, we took this example circuit, and we fed as input cosine of omega t. We have an R and a C, and let's say we cared about the output response, and we cared about the capacitor voltage. What we talked about was focused on the sinusoidal steady state response. And what that meant was, first of all, focus on steady state. Okay, in other words, just to capture the steady state behavior when t goes to infinity, okay, after a long period of time. And for most of the circuits that we consider, because of the R or presence of any resistance, the homogeneous response usually would die out because the homogeneous response is usually of the form minus t by tau. Okay? And as t goes to infinity, this term tends to go to 0. Okay, so we're just looking at the steady state, and therefore we can, because of the circuits to look at, we can ignore the homogeneous response. So all we're left to do is to find the particular response to sinusoids of this form. And second was focus on sinusoids. Okay, so he said, and the reason for this was that, let's say we did not care particularly what happened when I just turned on my amplifier. Okay, when I just turned on my amplifier, oftentimes you see some distorted sound coming out for a few seconds, and then you hear the much clearer sound. And that initial part is due to the transient response, and let's say we don't care about that. We care about the steady state. And second, we focus on sinusoids because based on the Fourier series experience that you've had previously, we can represent repeated signals as a sum of, as a sum of sines. And therefore, it's important to understand the behavior of these circuits when the input is a sinusoid. And what was important was this introduced a new way of looking at circuits, and that was the frequency viewpoint. Okay? When we looked at transient responses, we plotted functions or responses as a function of time. And when we look at sinusoidal steady state, it becomes interesting to plot the response as a function of the frequency, function of omega. Okay? So what I'll do is let me draw a little chart for you to sort of visualize the various processes we've been going through. So we can liken obtaining the sinusoidal steady state response to following these steps. So here's my input, and what I did as a first step was fed my input to a usual circuit model. Okay, my elements were lumped elements, built the circuit, and wrote down the VI relationships for the element. As a second step, I set up the differential equation. Okay, so this was the first of 4 steps. Set up my differential equation, and then the path that I took first was fraught with the real nightmarish trig. By the end of the day, it would still yield an answer. It would be a nightmare, but I would get something cosine omega t plus something, some phase. Okay, I could grunge through the trig, and I gave up halfway in class here. But you could grunge through it if you like, and you would get the answer to be some sinusoid with some amplitude, okay, and some phase. Okay, so Vi cosine omega t would produce a response that was something cosine omega t plus some phase. So we said that this was too painful, so let's punt this. And instead, what we said we do is take a detour. Okay, take a easier path. And the easier path looked like this. I said, let's sneak in Vi e to the j omega t drive. Okay? That is, just imagine, do the math as if you had fed in not a Vi cosine omega t, but a Vi e to the j omega t. Okay? And from Euler's relation, you know that the real part of this is Vi cosine of omega t. Okay, so we said that I'm going to sneak in this thing, find the response, and just take the real part of that, because the real part of the input gives me this. So this is my sneaky path, and what I did there, as soon as I fed in e to the j omega t, because of the property of exponentials, the e to the j omega t cancelled out in my equation, and what was left was some fairly simple complex algebra. Okay? And at the end of the day, after I grunched through some fairly simple complex algebra, I ended up with some response that looked like this, some Vp e to the j omega t. What I would find is that for the input Vi e to the j omega t, okay, I would get a response Vp e to the j omega t. Okay? And then what I said we do is take the real part. Why take the real part? Because this is a sneaky input. The input I really care about is the real part of the sneaky input. Okay? So this is my sneaky output. And what I care about is the real part of the sneaky output. Okay? So that was sort of the inverse superposition argument that I made on Tuesday, that if what I care about is the real part of this input, then I just take the real part and get the output that I care about. So I take the real part, and notice that Vp here in the examples we did an RC example, and the Vp here was a complex number. Okay, so I can represent that complex number as in many ways. This is e to the j omega t. So I could represent Vp in an amplitude, as a phasor. Okay, in essentially polar coordinates. So I can say that would be equivalent to Vp e to the j angle Vp. Okay, so Vp is a complex number. So if you look at the complex appendix in your course notes, I can represent a complex number as an amplitude multiplied by e raised to j times some phase. Okay? It's a simple complex algebra. And then what I could do here is take the real part of that. And when I took the real part of that, what came about was that this was simply Vp. Okay, notice that the angle Vp goes in here, so it becomes j times omega t plus angle Vp. So it's Vp amplitude times e raised to j omega t plus j angle Vp. And the real part of that is simply Vp cosine of that stuff. Okay, so what I end up getting here is Vp cosine omega t plus Vp. The cool thing to notice was that once I found out this response here, I could immediately write down the output based on Vp. Okay, so in other words, once I had Vp, I could stop right there in my math. Okay, I got Vp very quickly here. This step produced Vp very quickly. Okay, after two algebraic steps. And then from here, I could directly write down the answer as a modulus of Vp cosine omega t plus angle Vp. Boom, right there. Okay, so this was a much shorter path. Okay, and here I just described to you how this yields an expression for Vp and angle Vp. And for our example, Vp was 1 divided by 1 plus j omega RC. Okay, and we oftentimes write a shorthand notation 1 plus SRC, where S is simply j omega. Okay, we'll commonly jump back and forth between the shorthand notation S and j omega. Okay, S has another fundamental significance we will learn about in future courses, but for now, S is simply a short form for j omega. So this was the path that we took, and the hard path, the easier path. Today, I'm going to claim that even this was too hard. Okay, there's an even easier path. And today what I'm going to show you is that starting here, we're going to take one step and get here. Okay, I'm going to show you today that we won't do this, we won't do this, not this, not this, none of this. Okay, one step, and then we're going to get the answer. Okay, so let's do that. So before we jump into the impedance method and go into doing that, I'd just like to plot for you this function here so we can understand a little bit better exactly what is going on. So as I mentioned to you, the output V naught for our circuit there was simply Vp cosine of omega t plus angle Vp. All right? And, oh, that's Vp, so this one should be Vi here. Okay, I'm showing you Vp, so there's a Vi in there. Okay, so Vp divided by Vi is simply 1 by 1 plus j omega Rc. So this is a complex number, and it is simply a number that when multiplied with Vi gives me the output. Okay, this is also called a transfer function and represented as h of j omega. Okay, so this guy is a transfer function, much like the amplification of my gain of my amplifier, which when multiplied by the input gave me the output. This guy is a complex multiplier, which when multiplied by Vi gives me Vp, and as such we call it a transfer function h of j omega. And we can plot this function. Notice that this is a function of omega. Remember, we're taking the time domain, we're taking the frequency domain view. So where has time vanished? Remember that we're taking the steady state view. Okay, so we're saying in the steady state, if I wait long enough, this is how my circuit is going to behave. This is how my circuit is going to behave. Okay? And the transient responses have died away, and I have time in my output here. Okay, so my output is a cosine. But that in itself is not very interesting. It's a cosine of some amplitude and has some phase. So what we're going to plot is, we're going to plot this property here, Vp, as a function of the frequency. Okay, Vp is frequency dependent. Okay, so as an example, I can plot the absolute value of Vp Vi, the modulus of that, and versus omega. And notice that when omega is 0, again, intuitive ways of plotting this is to look at the value at 0 and look at the value at large omega. For small omega, omega close to 0, this is 1. So it starts off here. And when omega is very large, okay, then it's much bigger than 1 here. So this goes down so far away. This one looks like 1 by omega Rc. Okay, and this function, assuming I have linear scales on my x and y axes, looks like this. We also commonly plot this using log-log scales, and when you do log-log scales, you get a straight line here, and then you actually get a straight line of slope -1 because the log of this gives you a line with a constant slope, and it's a slope of -1, so it becomes a straight line going down. The other interesting thing to realize is that the magnitude, this magnitude is simply 1 by 1 plus omega squared r squared c squared, square root of this. Okay, that's the magnitude here. And notice that when omega is 1 by Rc, okay, when omega equals 1 by Rc, this thing in the denominator becomes 1 by square root of 2. Okay, so somewhere here, when omega equals 1 by Rc, the output is 1 by square root 2 times the input. It's an interesting point, and this is called the break frequency. Okay, you can view it as a frequency where I'm getting this transition from 1 to a lower value, and it's where the output is 1 by square root 2 times the value of the input. Okay, now, so now you can think back on the demo we showed you earlier, and in the demo, remember that as I increased the frequency of my input sinusoid, the output kept becoming smaller and smaller and smaller. Okay, and you notice that you can see this dying out or decaying of the amplitude as I increase my omega. So let me go back and what we've done is that we're going to apply a bunch of sinusoids to the same circuit, okay, and plot the frequency response, the output, the ratio of the output versus input as a function of frequency, and keep applying a variety of frequencies. Okay, so you can listen to the frequencies as they go by, and we'll plot the amplitude up on the screen for you. So just for fun, we're going to play frequencies between, say, 10 hertz, between 10 hertz and 20 kilohertz, and it'll be fun for you to figure out at what point you stop hearing the frequencies. Okay, we're going to play from 10 hertz to 20 kilohertz and figure out where your ears cut out. That will tell you what the break frequency of your ear is. So you can see the amplitude being articulated. The bottom figure is the phase. This is the frequency axis. This is the amplitude. Log scales. I'm not sure about you, but I can't hear anymore. So if you bring your canine friends to class, it's quite possible that they go berserk somewhere here. As I promised you, when we plot this in a log scale, I get a straight line here and a straight line there as well. And the bottom line gives you the phase. Okay? Now, what you can also do is you can also go to WebSim. WebSim is now linked on your course homepage. You can go to WebSim and you can play with various L and C and R values. And if you plot frequency response, if you click on the frequency response button, boom, it will give you frequency responses for your circuit that look exactly like that. Okay, you can go and play around with that. Okay, thank you. All right. So as a next step, I promised to show you an easier path, and let's build some insight. Okay, is there a simpler way to get where we would like to get? Okay, in particular, is there a simpler way to get VP? Okay, let's focus on VP. Why VP? Because, remember, VP was the amplitude, the complex amplitude of e to the j omega t. Okay? And once I know VP, then I know this expression here. Also notice that this here, the denominator, is simply the characteristic equation for, I wonder how many of you noticed it, it's simply the characteristic equation for the RC circuit. Okay, so if I can write down VP, I can write down the characteristic equation. It will be in the denominator. I can also write down the frequency response very easily by taking the magnitude and phase of VP. Okay, so VP has all the information humankind needs for that sort of for those circuits. So is there a simpler way to get VP? To build some insight, let's go ahead and write down. Let's stare at this for a while longer and see if if light bulbs go off in our minds. So I can write this as, I just replace a shorthand notation for j omega. And I simply divide by SC throughout. So I get VI times I simply divide by SC throughout is VI. So you have 1 by SC, 1 by SC plus R. Light bulbs beginning to go off? So the form we have here is it's 1 divided by SC, some function of my capacitance divided by something related to my capacitance plus R. So this is VI, okay, VI multiplied by something connected to capacitance divided by something connected to capacitance plus R. And remember your circuit. What is that reminiscent of? What does that remind you of? Voltage divider. There's some voltage divider thing going on here. I just can't quite pin it. Okay, something about the capacitor plus resistor, some voltage divider thingamajig happening here. Okay, so we'll try to figure that out. So what I'm going to do is replace those terms with something called ZC plus ZR. Okay, so if I can find out the ZC somehow, and the ZR and ZC somehow, I can write down VP by inspection by the voltage divider action. Okay, by some generalization of the good old Ohm's law that I know about. Okay, let's proceed further and see if we can make some kind of a connection between this and this. If I can make that connection, then boom, I'm done. I just use voltage dividers and I'm home. Okay, so let's play around and see. There's something in there. Okay, by now you should know that we're very close. Okay, there's something going on in there. I just need to get that spark. I just need to make that spark so it can bridge the gap between something that's really easy versus where I am. So let's take a look at the resistor. Okay, so I have my resistor with the voltage VR across it and a current IR. Okay, supposing, remember, to get sinusoidal steady state, we're going to be dealing with the drives of the form VI e to the j omega t, exponential drives. Okay, and by taking the real part, I know I get the input, and the real part of the output gives me the actual output. So let's say my IR is simply IR e to the ST, and my VR is VR e to the ST. Okay? The S is, again, a shorthand notation for j omega. So if my current is IR e to the ST of the form, exponential form shown there, and here's VR, I need to find out what relates VR and IR for the element relationship for the resistor to hold. Okay, in general, IR and VR are complex numbers. Okay, so for the resistor, I know that VR is simply R IR. Okay, and I substitute using my complex drives here. So it's VR ST is R E R I R E to the ST. You can just substituting for these drives, Ohm's law should apply. And I cancel off e to the ST, and so I get VR is R IR. Interesting. So for the resistor, I find that based on the fundamental principles of resistor action, the complex amplitude of the voltage simply relates to the complex amplitude of the input by the proportionality factor R. In other words, for the resistor, just as the time domain V and I were related by the proportionality constant R, the complex amplitudes VR and IR are also related in the same way. Okay? That's interesting. Now let's look at the capacitor. some current IC flowing through it, and a voltage VC. Let's say the current is IC e to the ST, and the voltage is VC e to the ST. Okay, let's plug these into the element law for the capacitor and see if we can find out a way of relating VC and IC. Okay, so I substitute. So I know that IC is simply C dVC dt. Okay, so I replace this with IC e to the ST is C d by dt of VC e to the ST. Okay, which is simply IC e to the ST C S VC e to the ST. Okay, so I can cancel this out again. Interesting. So I see that I get to be C S VC. Very interesting. What was interesting here? Notice that in the time domain, IC equals C dVC dt. It's the element law for the capacitor. So I said, let's use exponential drives, IC e to the ST, VC e to the ST. Let's use an exponential drive and try to find out what the relationship between the complex amplitudes are. I plug them in, and what do I find? I find that if my input is VC e to the ST, and VC is the amplitude of the input, then the current is simply given by something multiplied VC. Okay? It's very similar in form to what I saw here. So the resistor was VR equals RIR. For the capacitor, VC is simply equal to IC divided by SC. Okay, so 1 divided by SC kind of plays the role of R. In other words, the complex amplitudes of around the capacitor are related by VC equals some constant times IC. Okay, almost like a funny Ohm's law kind of relationship when VC and IC are complex amplitudes. Okay? For the inductor, in the same way, IL, VL, and L. Let's say IL is IL e to the ST, and VL is VL e to the ST. Let's substitute the values for the inductor into its element relationship as well. So I know that VL is L d IL dt. So therefore, substituting the complex amplitudes is L, and dIL dt will simply be IL S e to the S T. So cancel out the exponentials. So the reason we're able to do all of this is simply the remarkable beauty of exponentials. But exponentials are absolutely stunningly beautiful. And the reason is that when I differentiate them, what I get back is the exponential times some constant, and the constant was in its numerator multiplying t. And that's the beauty of exponentials. If this was a sine, then I get a cosine and a sine. With exponentials, these cancel out, and what I'm left to it is something that is LS VL, LSIL. Again, for the inductor, the voltage across the inductor relates to some constant times, LS here, times IL. This is absolutely stunning, okay? And almost looks like a form of Ohm's law here. What I'm going to do is, let's give this the name ZR. Okay, let's give this 1 by SC the name ZC, and let's give this the name ZL. Because it kind of behaves like a resistor. Okay, so the resistor simply becomes ZR, and 1 by SC behaves like a resistor, so I call it ZC, and this is a ZL. Okay, these are called impedances. Okay? So in other words, for a capacitor, as far as complex inputs and outputs are concerned, so VC and IC is fed to it, the capacitor can be replaced by an impedance ZC, where I can write the relationship between VC and IC as VC equals ZC IC. Okay, where ZC is simply 1 by SC. Similarly, for an inductor, I can write its impedance ZL as SL, and I get VL equals ZL IL. Okay, and finally for a resistor, it's pretty simple. Okay, so what I'm saying is that when I limit, if I'm in the region of the playground, okay, if I constrain myself in the region of the playground where my inputs are complex, my inputs are something Vi e to the j omega t, okay, are exponentials in that little region of the playground now. I've been focusing more and more on small parts of the playground, so I'm kind of boxed in right now. So in that region of the playground, this applies. Okay? So in that region of the playground, I can replace resistors by impedances, capacitors with impedances of value 1 by SC. Okay? And within that playground, the beauty of analysis there is that in that region of the playground where where the inputs are of the form Vi e to the ST, it turns out that the element laws are simply generalizations of Ohm's law. And that is absolutely stunning. Okay, I mean, it's one of the biggest, one of those, hallelujah moments in learning circuits. This is really big. And I think this is, almost as big as the realization that you can take a nonlinear circuit, operate it at a given operating point, and then if you sit around doing the Zen thing, looking at small perturbations in there, okay, those are going to be linearly related. Okay, this is one of the big hallelujah moments in 6002, and this is of the same magnitude as the small signal response being linear. Okay, it's something that's completely, non-intuitive. Okay, which is something that you just would not have known until you've seen it happen. Same way here. This is very important, so I'll repeat it again. So now I've boxed myself into this small region of the playground where all I care about is sinusoidal inputs and steady state responses. Okay? So there I focus on complex inputs, Vi e to the j omega t. All right? And I've just shown you that I can replace inductors, capacitors, and resistors with their impedances. And the amplitudes of the corresponding signals around them are related by just a simple Ohm's law-like relationship using impedances. But I'm still boxed into this playground, right? In my playground, it's all about e to the I j omega t. E to the I j omega t is implicit everywhere. I just don't show it. So if I want to talk to somebody else outside, so within MIT in this small region, it's all e to the I j omega t in there. If I want to talk to somebody outside, get out of MIT, get out of this playground, what else do I have to do? I have to take the real part. Don't forget that. Okay, so remember that, take for example VC here. So VC is this. Okay, so implicit in all of this is that if I measure VC at some place, it's really going to be VC is going to be VC e to j omega t. And if I want the cosine, the real part, then I have to take a real part of this. And the real part of that will be VC cosine of omega t angle VC. Okay? This piece here kind of goes unsaid. Okay? We'll agree that we have to do it, but we'll just skip that step because it's obvious. Okay, we'll just deal with the VCs and VLs now. Okay, so the new notation I've subtly sneaked by you, and that notation looks like a big letter and a small letter. Okay, remember you've seen VL. This is a total behavior. You have seen VL. That's a small signal behavior. And now you see this, capital V, small l. We are very quickly running out of, oh, and we also have DC. For DC, we related them as, or operating point values as capital V, capital L. Okay, we have one thing left, so nobody go out there inventing something new, we get in trouble. So this is capital V, small l, and this is simply complex amplitude in this small boxed region of my playground where the good things happen and exponentials fly. Okay? So whenever someone gives you a variable, capital V, small l, remember it's a complex amplitude, a complex number, and you know how to get to the time domain from there. You take that number, take the real part, okay? Multiply that number by e to the j omega t, take the real part, which is tantamount to magnitude cosine omega t plus angle of that number. Actually, you know what? Let's set this up. Okay, so back to our example. Oh, I'm sorry, this is not good. This is my time domain circuit. So remember, this was my time domain circuit. VI input, VC output, I wanted to analyze this. So what I'm telling you now is let's box ourselves in this impedance playground. And in the impedance playground, the input becomes a complex amplitude of the input. My resistance gets replaced by a box, ZR. My capacitor gets replaced by a box, ZC. And the voltage I care about here is V small c. Okay? Where ZR equals R and ZC equals 1 by SC. And now, there we go. I can write down VC using a voltage divider action as VC is simply ZC divided by ZC plus ZR. Done. Times VI, of course. Okay? And that gives me 1 by SC divided by 1 by SC plus R. And multiplying throughout by SC, I get 1 plus SCR, where S is j omega. Just can't get any simpler. So how long did it take to do this? 30 seconds. Okay, when I spent a whole lecture on Tuesday grinding through, first trig, giving up halfway and collapsing, and then showing you the sneaky path, which is still pretty painful. But 30 seconds, boom. This stuff is spectacularly beautiful. The really cool thing here is that in this impedance domain, for linear circuits, all your good old tricks apply. Okay? Your Thevenin, Norton, your superposition, name it and it applies for this linear circuit. So if you close your eyes and make believe that ZR is like like an R, and simply apply all the techniques you learned so far in this linear playground. Just a little hack at the end where this is the complex amplitude. Okay? And if you want to go to the time domain part, then you do the usual thing. Modulus VC cosine omega t plus angle VC. Just remember that. That's the jump to get back to the time domain. So just to show you that this is not just works for one little rinky-dink circuit here, but let me take a more complicated circuit. Okay, if I believe in my own BS, I should be able to apply this example, apply this theory to my series RLC. Okay, the big, the big painful circuit that we did differential equations for about a week ago. Let's do it. So I have a inductor, a capacitor, and a resistor. Okay, and what I'm going to do is replace this with the impedance model. Input VI, so let's say this was VI, and let's say I cared about VR, LCR. The impedance model would simply be VI. So what's the impedance of an inductor? SL. And for the capacitor, it's 1 by SC. And for a resistor, it's simply R. It's VR. Okay? So, and just remember, if I can find out VR, then for an input cosine of the form VI cosine omega t, the output will be given by VR modulus cosine of omega t plus angle VR. Just remember this last step. But VR itself is trivially determined. It's the voltage divider action again times VI. And the voltage divider action is in the denominator, I sum these thingamajigs. So ZL plus ZC plus ZR. ZR in the numerator. And ZR is simply R. ZL is SL. ZC is 1 by SC. And R is R VI. Okay? And I multiply through by, in this particular situation, by SL, S divided by L. I want to get it in the same form as you've seen before. Multiply throughout by, in the numerator and denominator by SL. What do I get? I get RS divided by L. And out here, I end up getting S squared plus 1 by LC. And I get plus R divided by L S. I'm done. Look at that. Well, a little more than 30 seconds, maybe a minute. What's this? Where have you seen this before? The denominator of this expression here. Characteristic equation. Okay, for the series RLC, for the RLC. Remember I promised you in the beginning that when we come to the end of the day, using a simple 1 minute expression, I'm going to write down the characteristic equation. Boom! Here's what I get. Did somebody hear an echo in there? Okay. So notice that just by doing a simple voltage divider thingamajig, I got this expression, and now I can write down the frequency response by replacing S is equal to j omega. Even more beautiful, and what's even more stunningly pretty here is that, remember the intuitive method I taught you about. The characteristic equation gives you alpha, omega naught, omega d, and q. And based on those, you can sketch even the time domain response. So guess what? RLC circuits are passé now. You can just write this thing down and you're done. 30 seconds or less. Okay, no DEs, no trig, no nothing. Okay.